Hey everyone, welcome to the stream. Hi Spec Trey Chama, welcome to the stream. So today I want to talk a little about, well, not really talk about, I just wanted to look up stuff about lenses and play with lenses. So one thing I noticed, which is like in VR, is that when you have things like sniper scopes or not just sniper scopes, but like lenses in general. Like think about this in a game. Is there ever a game that has a magnifying glass in it that actually works? And the answer is no, there isn't, because it's difficult to make something like that, like a magnifying glass. Like imagine you want to do an investigation, you want to investigate. Well, how do you investigate without a magnifying glass? Well, you kind of can't. But I guess there's no games that really allow such a thing, and that was what I thought of, like what do lenses really do? Like how do they even work? So I just wanted to start out first by doing some stuff with a lens. So I got this here, got one of these. So here's I guess, oh, is this image okay? It's not distorted. It's distorted on my screen, but it's not on yours. But so I guess this is, well, it says 30x 21 millimeter. Oh, the reflections. But it's pretty interesting. I guess we'll start out by just trying to look at something real close up. So this has got some text on it, and I guess you can read it, but let's make it bigger. It's upside down. But there's some very interesting properties about this, which is like, well, I guess it's out of focus, but me who has glasses makes me see better, so great. Yeah, it does. But so see, you can see this makes it like you bring it closer and it gets bigger, but then it eventually gets out of focus. It's quite interesting. So you kind of wonder what's really happening here. And like if you wanted to model this, right, how could you make a magnifying glass in a game or something like that that actually does such a thing, right? Like you want to have a game. Imagine a game where you had one of these and you could like magnify stuff. In this case, right? And then like when you get further, stuff flips upside down, which is kind of crazy. I'm sure most of us know this whole like going upside down thing, but I feel like it's kind of crazy when it gets upside down. And then when you move it, it moves kind of like reverse. When you move this, it also moves reverse. Anyways, so that is that, and then also one more thing that I wanted to do. So one thing you can do with a lens is you can make a camera. So let me make a camera right now. It's actually really easy to make a camera. So take a look here, and that's just a table. And I hold this up and made a camera. See that right there? That's the image of a light fixture. So this right here is actually like I've built a camera. So if you put like a piece of film right there, then you could expose this and like record that image. But right now this is like it's just that. And it's quite interesting, right? Like how does this work? It's a camera. Well, there's also another camera, which is what like the phone camera. But if you bring it up higher, then I guess this is quite similar. If you wanted to, like, you know how you have the sun. If you were outside, I guess it's cloudy today because where I am, it's always cloudy. But if you had the sun, you could focus this, and when you create the image of the sun, it can burn stuff because it's that bright. Anyways, that was a little bit about lenses in real life. I think the biggest aspects of what makes it interesting is the like it gets bigger when you move it farther, right? If you put it right up against, it's like almost exactly the same size. Like it doesn't make it bigger at all. But then when you pull it further, it gets bigger. The further you are, the bigger it gets. And then eventually it does this thing where like, I guess it doesn't when it's close up because of this camera, but like it gets bigger and bigger, and then it flips. See? It's like this, and then it flips. Then it's upside down. I think that's pretty interesting. And then I wanted to do a thing, like, think about this when there's multiple objects. So let's say we were looking at, I guess we have these two things. I know I'm just playing around. See, if we wanted this thing to be upside down, but this thing to be right side up, right? It's quite interesting because, well, I guess this is right side up right now, right? We can see this is fine, and then that thing's upside down. So we can zoom in here, but then in the background, so it's not like, if you wanted to create like an effect, a magnifying glass effect, you can't just flip the whole, like, just take a picture and then flip it upside down and then put it in this where the lens is, like put the upside down version. But instead, you've got to do something where, see, this stuff that's close by is right side up, and the stuff that's far away is upside down. So it's kind of like, imagine capturing both of those at the same time. I don't know. Yeah, when you have a lens farther and farther away, it somehow gets smaller. Yeah, so I guess now that we're here, I wanted to do some stuff with the actual, draw some diagrams and stuff. So I learned a little bit about lenses in physics, but I never really thought about this stuff in details. Because usually when you go to school and you learn about this stuff, it's just like plug and chug. Like, all right, I know I learned the formulas. I'm going to plug the formulas in, and then it's just going to work. So let's grab a little bit of a drawing thing, and I'm going to draw a little. So OBS, we're going to go over to this. I'm going to do an Aggie. Okay. So here we are in the drawing, and what I know about lenses is what I read is you have a lens, which is like, ooh, I don't want these colors. Okay. A little smaller. And min size. Like that. Okay. Okay, perfect. So here is like a like the lens, like the one we're just looking at. And then here's the middle. Oh, I'm pretty bad at drawing. Haven't used this drawing tablet in a while. So here's the middle. And then, so the way, also I can finally stream. Spec Trade Chama, you can stream. So what are you going to stream? What kind of content are you going to make? Kind of curious what kind of stream you plan on doing. Okay, so basically a lens, the way it works is at the highest level, well, like what you know is that like lens, like the way you define a lens is like you have these lines that go in from the sides and then they go into the focal point and then they all focus down in the middle. Like this. In the middle. I streamed an hour ago. Also, maybe I'll just stream random stuff. Oh, I can check out your stream. All right, let's check out your stream. We're going to do a live reaction of your stream. OBS, where's OBS? Is this you? Oh, you got your face reveal. I don't see your stream. Where is it? It's missing. This is 4 days ago. All right, I'm gonna see this impossible flip though.
Let me show you some shit, bro. Look at that. Shoot. Wait. What happened?
It's not out yet somehow. Okay, yeah, I guess yeah. Sometimes there's a delay before your live stream like shows up, so I guess it's not out yet.
Come on. This is not edited because only cut. I don't cut. Anyways.
Well, I guess if it's not edited, even though it says it's an impossible flip, it's probably less difficult than it seems. See, like when you just did it that way, it like was falling, but then it like pulls itself back up. I think there's some physics concept here that that makes the bottle want to stand up. So the impossible flip seems like it's not actually that hard. Like, let's go back to where it like this one, right? Like it almost, but so you flipped it. See, yeah, maybe. Let's go with slow mo. Do we have 60? No, we don't have 60 FPS. Okay. See, it's like flat. Well, okay, this is the wrong one. All right, we're gonna watch the slow mo. See, it fell flat, but then it like flipped back up. You saw that, right? See, it was flat, and then it like bounced back up to be vertical. And then like it was almost, but then it fell over. Almost. Almost.
Oh, we've reached the back rooms. I'm joking. Pay attention to this. Come on. Pay attention to this shit. Pay attention to this shit. Yeah, like.
Oh, you got it right, but it was off the camera, so you have to do it again. Oh. See, it does try to stay up. I think you're giving it too much force, so that like, oh, there you go.
Let's go.
Oh, you got him. Let's go. Okay.
That's my hilarious attempts on doing that piece.
All right. Well, I'll have to check your live stream when it comes up. But for now, I guess, yeah. All right. Back to what I was doing earlier. So basically, this is the lens, and we have like this distance, which is the focal length, f, defined as f. So this is kind of a property of a lens, and then basically anything that goes through the focal point will just go out parallel, and then anything that goes like parallel will go to the focal point. So like I guess lenses are also symmetrical. I guess the ideal we're talking about perfect lenses, not real life lenses. So real life lenses might not work this well. So if on the other side we have a line going in parallel, then it will go to the focal point like this. So it'll work both ways. Now we can use this to kind of figure out the behavior with one more thing, which is that anything that goes through the middle of the lens, like you shoot light through the middle of the lens and it will just go straight. It will be unaffected no matter what angle you shoot it at. I guess like the exact middle is like this. But anyways, this is like sort of a thing how lenses work. And I don't really get it, but we'll figure some stuff out. So let's delete this. Oh, 69%. It's a good number. Oh, I guess you can't see that. Shit, why is it not working? Okay. Okay, so back to this, where we were at. So we want to think of like, how does a camera work? So we saw the camera earlier. Basically, we have the thing we're taking the picture of. Here's a lens. And then we have the thing we're taking a picture of, which is here. So let's say this is our light here. I think it's now out. Okay, let's check it. Hopefully. I don't see it. It's not in your uploads, not in your shorts. It's not in your videos. Yeah, sorry. It's not out yet. Blame Susan. Susan! God darn it. Okay. So what we're doing, we have this thing, and then here's the focal point, F. Right? The focal point, which I can only see it. Did you change your privacy settings? So this is F, the focal point. So we consider this, and then we shoot the beam here parallel, and then it goes through the focal point. Then we can also shoot a beam through the equivalent focal point on the other side, and then it'll go parallel, and then one through the middle, which also just happens that all these three beams line up. Now, why do all these three beams line up? Well, that's just because it does. Just because. Ah. Wow. Okay. So here we can see that this is, like, if we built a camera, this is the thing we're taking the picture of. The thing. This is our light. And then on the other side is the film. So we put the film here, and in this example, where's the example? Okay, OBS. So here, what we saw earlier is this would be the table on the bottom, and this, when it's lined up, that's a light, and this is a lens. So those are the items that we're looking at here. Okay, so back to where we were before. We want to find out how far each of these is. So like here is the film, and like, what is this distance? I guess this is a mystery, right? Where do these points converge? So I guess we'll do a little bit of math and figure it out. I know there's a formula that you can just look up, but I don't know. I guess it's a little tricky to look up the formula. So I know how do we do it exactly? We know this distance is, well, let's set this as 0, and this is h, height. So we have the height of the object, and then this is f, and we'll call this like, I guess we'll call this like D or something. And I don't know. Okay. So I guess we'll call this D1. And we'll call this like D2 or something. So we want to, I guess the ratio is just going to be these distances. Okay. So this, we just want to find the slope of the middle line, which is rise over run. So this one is y equals minus h over d1. And now this one goes vertical, and then it goes down through the focal point. So down through the focal point is rise over run, which is going to be h. The second equation is y equals the height, which is h, and then minus h over f. Okay, so we just need to solve these two equations, and then this will give us this, like, this will be like h2 or something. So let's go in here and solve these equations with a new brush. Okay, so I want to set these two to equal. So h over d1, h over d1 equals minus h over d1 equals h minus h over f. I just almost somehow lost my YouTube account. What happened? Equals minus equals h minus h over f. H minus h over f. Okay, so we'll just solve this equation for. Wait, what? Oh, right, I forgot. We have x we need to solve for times x, right? That's how you do an equation. Okay, so times x equals h minus h over f times x. So we bring these terms to one side, which is going to be h over f minus h over d1 times x equals h. So now we just say x equals h over f minus h over d1. Damn, I'm an idiot. What happened? Equals h over h times d1 plus f over d1f. These cancel, equals d1f over d1 plus f. I think. Is that right? Is that right? Did I do it right? No, it's minus f, right? Oh, I'm not very good at this. The eraser. Oh, okay. We can do brush. Make it small. Okay. So we do this, and it's going to be d1 minus f, right? I logged on my account to see my stream was really out and was wrong and didn't know YouTube password, then forgot the rest. Oh, no. Well, I guess you got back because you're still here. So I guess it's fine. I should leave this eraser. And I keep... Yeah, okay. I should just use my brush. Okay. So now we have equals D2. So I guess we can write this in the new form. So like here we just have the formula for D2 as a function of this. Is that right? Thank God, I'm never trying it again. I don't think that's right. I think I fucked. No, no, it is right. I think I just need to like that's like a different form. So if I rewrote it, or actually, I think if I kept this one, like 1 over I read it this way: 1/1 over f minus 1/d1 equals d2. So then I just flip the whole thing: 1/f minus. Oh no, I'm out of canvas. 1/f minus 1/d1 equals 1/d2. So 1/d1 plus 1/d2 equals 1/f. Thank God I've never tried that. Yeah, okay, well, it's fine. All right, so let me delete this whole thing and move on to the next part. So now we have this formula, which I guess works a few ways. So one over d1 minus 1 plus 1/d2 equals 1/f. That's right, right? At least what this says. Oh, it's minus, right? Is it minus? I guess it's minus, right? There's O and I, right? Okay. Well, I guess what this tells us a few things, but essentially we can use this to calculate a few things. But what I want to do is calculate the scenario where we have an object here, and then we have me here. Well, I guess here's the object, the object, a box. And there's me here looking at it, investigating, So I'm investigating, and I'm bringing this lens forward and backwards. So the question is, like, what do I see, right? Well, so I guess the way it's going to happen is that there's going to be a new image, either here upside down on this side, which is going to be a certain size, or a right side up version, which is going to be could be a right side up version here on the other side. Well, a little complicated, but let's drive this formula. So I guess what I want to know is, like, how big something actually is. And to know how big something is, there's kind of the idea of how big it is and how far away it is, right? So imagine we had this picture of, like, some buildings, right? You ever see that picture of like some person like this holding up the Statue of Liberty or something, or the Empire State Building, let's say. And then, so, like, we get this picture, right? And it's actually because this thing is far away, and it looks the same size as him because it's far away, but it's bigger. So in that sense, right? So we have, like, someone up close here, and we have the camera here, and it sees this person, and it can probably see, like, a building here at the same size as the person. So probably at a first approximation, we can say like size relatively equals, like, height over distance from camera. Just as a first approximation. So now let's go to this this thing and kind of get an idea of how big does this look to me here? How big does the new thing look on the other side of the magnifying glass. So let's go to our thin lens equation and say, right, so let's call this like L, I guess, distance from me. Then I guess we'll put the magnifying glass somewhere, which can be another distance, like M. Just say, let's make it M. Okay, M's not a great. Brain.exe has stopped responding. This isn't that complicated, right? It's just math. Well, you get this whole idea of, right, this. You ever see the pictures like person holding a building. Not like this perspective, right? Like this, right? Here we go. We got a nice stock photo here. What's a good one? Or like, I think probably like, where's a good one? Where's a good one? I guess it's always the leaning tower. My brain has become a mush. Leaning tower perspective person. Oh yeah, it's called forced perspective. That's what they call it. Yeah, here we go. Here we go. We got this person licking the this. I want this to be a new layer. Here we go. New layer, and then resize. Right. So the concept is, right, how does it look like this, where the tower is made to look the same size as the person, even though the tower is big, it's because it's farther away. So we do use this, I'm going to approximate it as this formula, I guess, because like that's how it's going to line up in the camera. So yes, let's get back to the thing. So let's call this should I call this M, or should I call it this? I think I'll call this M, because that's closer to like, let's just do everything from me, the smiling me. So no, I'll do it from the object. It'll make the whatever. It's not a big deal. Okay, I'll call this one M. Okay, so this distance is object L away. So now we're looking at the formula 1 over d1, well, equals 1 over f plus 1 over d2. Does it make sense? I guess if it's... does it make sense? How do we end up with negatives, right? Or I guess if one is right, okay, if something's smaller or bigger, right? If right, yeah, okay, this is fine. So we can say d1 equals d2 plus f over d over d2f. Okay, good enough. Which is, this is so this is d2 equals L minus M So d1 equals L minus m plus f over d2 over f times L minus m. Okay, so I have d1, which is this distance, d1. Now I want to understand how large, like how tall is it going to be? Is just going to be d2. So the new height, h2 equals simply h1 times, which I guess we don't really care about. Let's just say h1 is 1. So we're going to call h equals d1 over d2. Okay. And so all we have to do now is graph us h over distance. Distance is 1 is m minus d1 h over m minus d1. Okay, equals d1 over d2 divided by but we don't know, d1 and d2 are different things, right? d1 equals this. Oh wait, I guess if d1 equals this, then d1 over d2 is not any easier to calculate, actually. What is d2 again? Did I mix up d1 and d2? Okay. My brain is becoming mush too, actually. So d1 over d2 is equal to d2, of course, we defined as L minus m. Everything I see is Kirby now. Can I draw Kirby? You know, Kirby's kind of like Fuatani. There we go. Here's Kirby. Looks like a ball, right? Okay. d1 over d2 is, we just slap a d2 on here, which is L minus m. So it's going to be L minus m plus f over f times L minus m squared. Ouch. Okay. So it's going to be this, and then we just do divided by 1 minus d1, which is this, m minus d1. We just graph this thing as something like totally... Look at cute little Kirby. Yes. So we're going to go with this. So it's 1 minus m plus f divided by f times L minus m squared. We can just make f equals 1, and then m is going to be that thing, and then this is outside. It's m squared, and then times m minus d1, which is m minus 1 minus m plus f divided by f times 1 minus m. Okay. M Excellent. Let's graph this thing. Hopefully it doesn't choke on this big equation. So L is 1 minus M. And then we'll say F is like something smallish, right? Let's just say F is F equals 0.1. Okay. So 1 minus M plus 0.1 divided by this thing on the bottom, which is 0.1 times. My brain is now a melted mush of confused. It's okay, we're almost done. We just have to type this thing in. I don't even know what it means. I just like rammed this in. 0.1 times 1 minus M squared. 1 minus M squared times this thing, which is times M minus this thing. 1 minus M minus 1 minus M plus 0.1 divided by 0.1 times 1 minus M. 0.1 times 1 minus M. Okay, graph from 0 to 1. The y equals how do I graph something? Y equals this from 0 to 1. Okay. No. I don't want to integral. How do I graph something in this thing? I know there's a graphing, plotting and graphics. Plot function, specify plot. Okay, plot and then from. Okay. Plot this from M equals 0 to 1. There we go. This didn't work. I think I screwed it up somewhere because it's there should be something happening. Oh no, M is the other way, right? M is the distance from me, right? M is the distance from me. So actually I kind of want to do like from 0.9 to 1. Huh. I think I screwed it up. I must have screwed it up. I screwed it up. Can't believe it. Is this formula parsed right? It's like 0.1. This is what always happens when I do math. I'm always really bad at math. Like I just want to, because this is supposed to be like how big, the bigliness, like the bigness of how big it is. But it didn't work out because, well, the bigness is negative here, but like I don't have the positive bigness at the other side. I wonder if there's something degenerate. So if D1 is, imagine if D1 is negative, that would be like, I wonder if this is like 1 minus M squared is breaking it. So we have this function of d1. I'm just going to double check my work. d1 equals this, d2 plus f over d2 times f. This is a classic thing. Then we do d1 is 1 minus m plus f over f times 1 minus m, because that's d2 is 1 minus m, and then h is d1 over d2, d2 being 1 minus m. 45 minutes in, we're already in a big rabbit hole. Yeah, that's the point, right? So it's f times 1 minus m, and then it's 1 minus m plus f. Let's just graph this, h. Let's see if this is correct. Duplicate. See if h is correct. So we don't need this other thing. This gross thing at the end, we'll remove it. It appears that we have something wrong in the sense it's still not going in the other side. Like, what happens at the other side of 0.9? It's not like, because I think something should happen once this crosses the focal point. But nothing is happening, which is weird, because it just keeps getting bigger. So even this formula is wrong. I must have screwed it up. Let's just plot this one. This one. Let's plot this one. So let's remove the squared part. Huh. I guess, like, I don't even want to... Okay, I want to make this even simpler, which is... I'm just going to do this m plus f over m times f. From m equals 0 to 0.2. Did I even screw up this equation? Did I screw up this equation? Where's the hyper? I did the hyperphysics. I did this thing. So and then I do like 1 over this thing. It's 1 over that. Oh, it's upside down. It should be upside down version. I flipped this. This is reversed. This is reversed. Oh, I can't believe I screwed that up. It's d2f over d2 plus f. There we go. I can't believe I screwed that up. Right? Well, it still doesn't work. Equals 1 over this thing, right? So 1 over I just have a plus, so I don't see how it can go into the negatives. I'm actually like misinterpreting this question, misinterpreting this formula quite. I'm having a lot of trouble with this formula here. So I just want to know, like, I as a function of O, right? So like, how far is I as a function of how far is O? So I just need to invert this thing, right? So I is 1 over this thing. So I can just, like, let's just do it directly. I equals 1 over f is 0.1 plus 1 over m. Like, is this right? I wonder if if there really should be a minus. Like, if this was a minus, wouldn't it look a lot better? Like, doesn't this make more sense? Oh, is this formula wrong? Fuck it. This is oh, okay. This fucking gay ass sign convention. Okay. Okay. I freaking screwed up the sign convention too. Okay. No wonder nothing works. So this should be a minus. And then now everything should work. Maybe possibly. Okay. So freaking hyperphysics failed. Well, this is what gets you every time. Okay, so let's draw this thing again, and we'll just write this formula here, and we'll just check each step. So we're gonna see like how far is this thing. D1 is a function of D2. Is gonna plot that and make sure it works, which is D2 times F. So it's gonna be one minus M. Well, this part's gonna be different now, right? So it's gonna be we're gonna have to redo all this. So that part's still right. Okay. I didn't do the same sign convention. You know, when they draw this fucking picture, you think that like I is positive here, but really like in this picture I is negative. Just, you know. Anyways, so let's draw this is D1, which is 1 minus M minus F. Let's make sure this is right. I know nothing other than lens makes images smaller and smaller the farther and farther away. Well, so this is what we're going to figure out. Like, I'm making the formula to know exactly like how the bigness of the object depending on where the thing is, you know? Okay, so it's D2 times F over D2 minus F. Okay. So it's 0.1 times M over 1 over... Is it D2 minus F or is it D2 minus M minus 0.1? Okay. Just get my signs correct because like it's going to be one where I drew the picture. So if it's it should be the opposite because I want it to be I want my D to be positive just because the way I drew it. I want my D1 to be positive when oh, no. I want mine to be positive when it's far. No, yeah. Yeah, I want mine to be positive when it's far, and that's true because this is correct. And then yeah, I always do this like back of the envelope sort of thing. Okay, so let's erase this part. Okay, this should be my eraser. Okay. D1 equals D2, which is 1 minus M times F divided by D2 minus F. So it's 1 minus M minus F. Okay, we do the division, and then we do this is D1 divided by D2. D1 divided by D2 is just 1 minus M, so we cancel that out, so it's actually F over 1 minus M minus F. Excellent. All right, and then M is this, okay. Now we just need to H over M minus D1. Okay, so H over M minus D1. So we'll erase this whole part. This is just where it's going to get a little messy, but it shouldn't be a problem. So H is F over 1 minus M minus F times m minus d1, which is the messy part, 1 minus m times f over 1 minus m minus f. Okay. I always draw my fractions like this. They like the thing slopes up. You know, that's my way of drawing fractions. Okay, so we're gonna plug this in, and it's gonna look great. Just gonna plug it in blindly. F over, okay, so f is 0.1. 0.1 over 1 minus m minus f. Let's move this tab over 1 minus m minus f is 0.1 times 1 m minus 1 minus m times f over 1 minus m minus f, close, 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 plot. There we go. Wait, what? Oh, no, f is just 0.1. Okay. I don't think this is right either. I think I must have screwed it up again. Because, oh, no. This is right. No, there's two flips. There shouldn't be two flips. This shouldn't be symmetrical. Because really what we're expecting to get is there's the object, and when it's close, which is near 0.1, it gets bigger the farther you move it. Actually, I wonder if, no, there probably is a second flip, yeah. And then it gets bigger the farther you move it away. I don't know why it's negative. It gets bigger and bigger, and then it flips, and then it gets smaller and smaller. I don't think this is right, though. Like, this second thing doesn't sound right. Let me double check this thing. Did I screw it up again? So this part is, D1 is definitely right. And the H is D1 over D2, and D2 is just 1 minus M. So we just cancel that thing out. So this is fine. And we want to do H over M minus D1. Huh? Wait, how did I get this? Oh, H is this over M minus D1. Well, let me make sure H is right first. I think H shouldn't have this extra flip, so let's just grab this H, and it won't have this last thing. Because here we're just doing H over M minus D1, so we just delete the M minus D1 part, and we get what we're looking for. No? H is still wrong. It's H is still wrong, I think. Because H still needs to have its flip. I don't think it flips. YouTube just removed my live stream for child safe. What the heck? Why would they do that? Now I'll never be able to see it. Oh, Susan's coming for you. Spectre Chama, Susan's coming for you. It was good. It was good knowing you, but it might be over. It was good knowing you. You're gonna get carted off into the oblivion by Susan. Susan's gonna nuke you. Let me make sure D1 is right. And H is just D1 over D2. Wait. H is d1 over d2. Yeah, d2 is 1 minus m. In before band. Shit. Yeah. Susan's coming for ya. 1 minus m times f over 1 minus m minus f. Okay, so let's plot that. 1 minus m times f times 1 minus m times f over 1 minus m minus f. That should be, so this one should flip. It doesn't flip. I know this one flip. Shit, I lost my other. Why didn't this one flip? d2f over d2 minus f. So I know if I did it like this, times, like if I got rid of this, it should, I remember it flipped. It doesn't flip? From 0 to 0.09. It does flip. Okay, it just isn't graphed. How do I do my axes example? Plotting. And I want to do Wolfram alpha plot y-axis. Change y-axis range. Plot range is, okay. Let me just see if I can slap this in here. -1. I'm pissed about that though. I was just streaming. What could have happened that was not saved for me? I was just, what stuff were you doing? Oh, what the heck? I guess I want to do like plot this, and then I can do this, and then like close. What were you doing? What stuff specifically were you doing? Wolfram language plot. Wolfram else is kind of shit. Oh, there, yeah, okay. This fucking piece of garbage. I need like a real plotting tool. Graph function plotter online. If this doesn't work, I'm gonna have to go to like Excel or graphing calculator. Okay, this should do it. There we go. Okay, this one actually works pretty well. Okay, let's not use that shit. Yeah, okay, this is way better than that other shit. What stuff were you doing, Spectre? Okay, so this part's fine. Let's actually like copy paste this whole big ass thing. So let's copy paste this whole big ass thing minus the last part. This. So this is H. Why doesn't it like it? Oh, yeah. Okay, so this one looks about right, actually. So H is about right, where really close to H is just 1, and then it like grows like that. Okay, so this is looking good. This is looking real good, and now we want to do the full. I guess the other thing is this thing, which is I have no idea what's that formula again? M minus this is D1. Okay, so D1 is this. Oh, I guess it does flip when the D1 goes behind your face. Yeah. It's actually really interesting that this plot is symmetrical. Never would have thought it would be symmetrical, actually. But I guess it's like the part to the left isn't really valid. Playing Terraria, Geometry Dash, looking at my stream, getting annoyed from my brother on Steam. What is the problem with YouTube? Yeah, what's the problem with Susan? What's your problem, Susan? Does that mean your channel is deleted? Okay, you're still here, I guess, but I guess you just got your one stream nuked. We'll never be able to see. We'll never be able to see your live stream ever again. Not my channel, it was my stream. Okay, well that's better than getting your channel nuked. I guess we won't you won't be destroyed. You know, when Susan's on your butt, just run away. Don't fight it, because Susan's mean and nasty. Susan's mean and nasty. So that's quite interesting, actually. Let's take a look at this effect, because it seems like halfway through, it's gonna get bigger. It's gonna like see, because like once it flips, it's gonna get smaller. YouTube moderation is kind of bad. Yeah. YouTube moderation is really bad. So what happens is, like, what we expect is first we see this thing, the size. So it starts at size exactly 1, and then when you move the magnifying glass a little farther from the object, it gets super big, like super fast. It gets freaking massive, and then it flips. And when it flips, like it's gonna flip and start super big as soon as it flips, and then get small, and then right at the middle, it'll stop getting smaller and actually get bigger. So let's go back to this thing, 192, and look at the camera again. 168. Oh, I'm revealing my IP. 12.119:8080. User password is 12345. Oh, I have this on another window. I had it on a different window. Yeah, okay, I don't need to do that on Chrome. Let's grab OBS and we'll go over to here. So what it was showing is that halfway between, so let's say we have this object and we want it, like we bring it up and it gets bigger and then it flips. I guess it's kind of already too big though, but yeah, because it's already pretty big in here. Let's bring it farther. Let's point it at over here. Am I back? Can you hear me? Am I back? My Ronanet. I accidentally my entire Ronanet. Okay, so back to where we were earlier. What it was showing is that the thing will get. Did my phone? Oh, my phone switched off of the Ronanet. I'm going to switch my phone back to the Ronanet, and then connect back to the phone. Oops. Back. I'm back. I thought you were streaming. No, I'm still here. I just reached I have a big tangle of wires under this table that you don't see. Okay, 119. All right, we're gonna be right back here. She's gone. Tachi-chama, she's not gone. Just killed by the Rona. Okay, so what we were looking at is let's look at that little USB back there that I put next to the salt shaker. We've got some sea salt. So here we can see, we look at this and then it's small. I don't know if you can hear me. Okay, so we're gonna look at the salt shaker, and oh, it's already pretty big. So it's small, and it gets bigger. Oh, and it's big, it gets real big, and then it flips. It flips. So then we have this salt shaker, and then it gets smaller and smaller, and smaller and smaller and smaller. And then halfway it should start getting bigger. Okay, maybe this formula doesn't really work past halfway. Can you focus on that? Focus on that. It is a little bigger. Like, it does start getting a little bigger, like, partway through. See, so, like, the flip image gets smaller and smaller and smaller. And this is about halfway. Like, see how small the flipped image is? I bring it up, and, like, the flipped image is definitely bigger. Not, like, bigger relative to the magnifying glass, but, like, relative to the size of the screen. You can see that, like, it's, like, that big right now. But then we bring it up, and it's... Well, let's look at how big the salt shaker is, right? So the salt shaker is about this big here, and then we bring it away towards the middle where it should be the smallest, and look how small the salt shaker is. So it's actually the middle where the salt shaker is the smallest. And my Wi-Fi is being a little shit. No, it was my fault that the stream stopped working. I unplugged my internet. So looking at the size of the salt shaker, right? It's right in the middle at its smallest point. It's just this big. But when I bring it closer, it actually gets this big. The salt shaker is this big. And then it gets smaller right in the middle, the smallest salt shaker. And then like it gets bigger again as it gets closer. I'm lagging. Oh no, is anyone else lagging? How's the stream going for everyone? So actually, like, I think that's really cool. I never really even expected it to go this way, where it's just like the formula says, which I didn't look at, but which I just made the formula for, is that the middle part is where it's the smallest, and then you bring it past the middle, and the picture gets bigger, and then you bring it past the middle. So when the flipped image is the smallest, exactly when the magnifying glass is exactly halfway in between. It's cool. This is math. This is physics, right? I'm gonna do that again. Oh no, I guess you can't see it right now. That's so cool. It's just like the formula. Just like the formula. I can't believe it worked. Well, I guess I should believe it worked because, like, why shouldn't it work? I did the math correctly. Let's read the text. Grinder. Homo. See, so we look at that grinder, and it gets big and big and big and huge. Look at the small text. Bigger, huge, and it flips, and then gets small. Gets real small. Gets tiny. And it gets bigger again. I guess it's like by the time it gets bigger, it's already fuzzy, but like definitely you can see the salt shaker start expanding as we get closer. My Wi-Fi is just bad though. Yeah, well, I guess if any, oh, this was a little cut off, but I guess it's fine. You probably saw what I was trying to show. Okay, so that was that. Wow, this is a cool graphing calculator though. All right, let's go back to Chrome. OBS. So we figured out a little bit about how it gets flipped and where it gets flipped, and then like how it gets small right in the middle. Gets small right in the middle. That's still so crazy, I feel like. And it's actually, well, I guess if we change this focal length instead of 0.1, we can make it like 0.3 3. Like if we made this bigger, oops. Oh no. Okay, there we go. I didn't lose it. I wish I could like make this thing like, well, actually let's copy paste it. So like see like what it's different if we have like a different magnifying glass. Interesting. All right, let's delete this one. Five. Can I make a slider? Like if, oh, I guess this thing might let me do like F slider. Add slider for F. Oh, this thing is so cool. Dude. All right, so as I change F, it, of course, I guess F should be like these very small values. Can I change the range of this? 0 to 0.5. Good. Yeah, it happens. The internet's kind of bad sometimes. So when F is pretty short, then we see a really small thing in the middle, and then it's pretty flat. I guess we see this flat area, which is actually quite interesting, where the size of the thing, like, I guess that's what we see if you look at something really far away. Let me see if there's something I can safely look at really far away. I guess you can look at my kitchen. But when you're in this flat area, it doesn't actually affect the size very much, where you move it back and forth. And then if F is small, so that's for something really far away. But if F is big, interestingly, the middle part, the flipped part is like it's still big in the middle. And I guess the F number is kind of a concept you'd expect to see in photography too. So I think I'm sure this has a bit of a relationship with photography. You know, when you buy a camera, it's like, oh yeah, it's got a F equals 35 millimeters, and I'm like, what does that even mean? It means something like this, right? Math, because when you do take the picture in your camera, like if you bought a real camera, it would be flipped. It's in the upside down region. It's like you're somewhere in here. Well, of course, I think a real camera is a little bit more tricky than just a simple lens. I think when you get something like a telescopic lens, it's doing some... no, I wonder... Actually, no. I think you just changed the F number. So imagine, right, you got the film... Oh, no. When we're not looking at this when we're talking about a camera, right? So when we're talking about camera, we're talking about... camera's like a thick lens. It makes things more complicated. Let's not talk about F numbers in cameras. Okay, so that was this. Yeah, look, when you do some physics and then like after you're done doing work, it always looks so cool. You got your formulas on the blackboard. You're like, wow, look at those formulas. And really, it's just all simple, really basic math. But you really think like, oh, I'm educated. I know physics. Look how smart I am. And we got Kirby right here. Look, we even got Kirby. Okay. So that was the single lens that I wanted to do. So that's like the bigness of how the bigness is affected by where you, like when you move the lens. So I think there's one more thing I wanted to do, which is sort of something that I haven't really explored. Let's make a new Aggie. But let's how should I do this? I think the thing is that when you look at stuff in a lens, it's actually a different shape. So let's say we're magnifying this thing. Let me go back to the camera. Let's go back to the camera. Where were we? OBS. Go back to the camera. The camera. Okay. So when we look at this, right, we see that this object is like pretty normal shaped, right? It's got straight lines and all that. But if we looked at this through the magnifying glass, oh, I can't get a good angle. Oh shit! You didn't see anything, did you? Foot reps. Okay, so where we were is we're looking at this object and it looks, we see that it's this shape. But if we try to look at it through a magnifying glass, it actually look quite different in the sense of what shape it had, I think. I think one interesting thing to look at is, interestingly, these lines are parallel, right? This thing is, well, they're not parallel. See, in perspective, these lines are actually converging, right? Like we know a little bit about perspective is that these parallel lines converge at the final point. Yet when we look at it through a magnifying glass, it's very odd because they actually diverge, right? Look at that in the sense that they're actually getting farther apart. They're getting wider. Isn't that weird? No. Gyro. Oh, I guess. Yeah. No, you didn't see anything, right? That's what you mean. So isn't that weird that when you look at it through a magnifying glass, the shape is actually changed, like drastically, in the sense that it's not a perspective anymore because it's, well, like, you're not looking at this object anymore because it's getting bigger farther away, right? So here, right, you see these lines. Let's go to, we're going to draw a little bit of a demonstration back in the Aggie. Start drawing. So, like, we probably know a little bit about the concept of a single point perspective. So you do a single point in the middle. If you want to do art, you're like, oh, let's make a table. So you draw the lines that like go towards here, and you're like, oh, okay, we draw a table here with some legs like this, and they like, and then we draw like a cube over here, floating in the sky. And then you draw those lines like this. Like this is art, right? And then you draw this, and then you draw another cube, draw another cube up here, like this. And then you draw the lines like art. Is this pause? Oh shit! This is like I know a picture like that. No, I'm not trying to like imitate anything like that, but I know what you mean. Right? You draw the cube like this, pointing towards the center, and then like, if you want to make these cubes float, you just erase the middle parts. So make a bigger eraser as another brush. Right, so in like reality, like it's not exactly like this level of perspective, but you can kind of see how these lines converge. And it was the same when we looked at that box, right? So we looked at that box and we saw the lines converge when they go farther on like that. Yet when we looked at it through the magnifying glass, right, through our investigation, right, our magnifying glass like this, we actually saw a fully different image of the lines. We have our box and the lines actually diverge somehow, right? and then like there was the hinge, right? But so in the magnifying glass, it's like this, but in the regular, it's converging towards towards the center, right? Towards the point of perspective. So I think that that's like a very interesting idea. Like, how did this happen? How did we get this sort of shape distortion? And I think we can use this we can use this sort of concept again. So we'll use this conception as we looked at previously of size equals h over distance, right? So let's look at if we look at this gap, right, in the same perspective, we have the camera. We have the camera and how do I draw a nice camera? There we go, nice camera. We have the camera and it's looking at like a couple parallel boxes that are separated. Oh, well, this is, let's say it's top view. Top. Hi, Pocket Music Chama. Welcome to the stream. Hey, cool stream topic. Yeah, did you miss the previous stuff? I guess I don't know if you were here for it, right? We learned about stuff. But yeah, did you see the divergence? I can if you weren't here for it. I think this image is really cool though. The freaking diverging lines. This one. So where see they're in perspective, they get closer together. They're going towards a single point, like all going like this way towards the middle. Yet with the magnifying glass, with magnification, they go apart. Anyways, wacky. Yeah, it's pretty wacky. So of course this is just a very rough conception. But if we're looking at, let's say, the top view, so let's see top view, and we have these two parallel boxes. Let's say we have this box and this box. So if we look at this conception of like how separated are they, right? So we have this one here right at the beginning and we have this one here at the end, right? So screen is black. Oh, yes. Sorry. So if we go back to this idea, right? Look at these where, like, I guess the box, like it is a box, right? But the boxes that are farther, right? Like let's say we continued this box train along here. This box that's farther is smaller. And if we looked, like this box is the same size as the one in front, right? This one, same real size. Same real size, but like this one's smaller on the camera. Like if we just look at this versus like this one's really big on the camera, but they're the same real size in real life, right? If we did this like, lined up, right? So it's quite interesting to think about it that way. This box is much bigger to the camera. And so this is like the whole convergence as things get farther away thing. We can go back to our formula of size equals size on the camera. Like size on the screen is h over distance. So h is constant. H is constant, and this is distance. So we would get farther from the camera. So if we just say, we'll plot a real quick, easy one. Close all this extra tabs. Plot a real quick, easy one, right? It's just 1 over distance, 1 over distance, x. Okay, so as it gets farther away from the camera, like the spacing on the screen gets smaller and smaller. So let's consider this again now. When we look at it through a magnifying glass. I need a new Aggie. Well, we'll keep this one for posterior. I guess since these are Aggies, you can also check them out. This is a collaborative study group, right? So what we had like the magnifying glass, and we have these bars, these parallel lines, right? Let's say this one's at 0, right at the middle, and we have these parallel lines, and we have a camera here, us here. So bad at drawing faces. Anyways, here's us, and we're looking here, and we want to see, like, right, with no lens, these ones will obviously look like they're converging on the camera, like on the screen, right? On the screen. Let's say we had a camera. Oh, big ass camera. But let's take a look at what they're going to actually behave at relative to the lens, like how big these are. So this is a fixed distance, and then we have f, which is also a fixed distance. Let's just set these, like, again, what we had before, like f equals 0.1, or well, actually the thing that let us parameterize, actually, because we're using this new Desmos grapher. So let's go and draw a little. So we have this previous formula from the previous one, which is that I guess we have d1, d1. So we're going to have this same formula, distance. Distance equals this thing. Let's call this will be our new L, I guess. L minus, we'll just make 1. We'll make L equals 1, because that doesn't really change a parameter. We only have one parameter that's really needs to be parameterized. Will be L 1 minus D2. No, D1. D1. We're doing the same formulation we did before. Of course, we don't have any L minus M's, right? Which is going to be a function of D2. 1 minus D1, and then is just 1 minus D1. Okay, and now we have H equals what we had before, D1 over D2, D1 over D2, and we also have our previous formulation, which is D1 equals D2F over D2 minus F. D1 equals D2F over D2 minus F. Okay, so we have this formulation, D2 minus F. So let's come up with this, and we're going to replot this out again. So so we'll just calculate size equals h over distance. Oh, my handwriting is so bad. Okay, so h is d1 over d2, so it's just f over d2f is h times 1 over distance equals times 1 over 1 minus d1. This is actually quite a bit simpler. 1 minus d1, okay, 1 minus d1 we know, of course, we need to substitute it in, which is d2f over d2 minus f. And there's no point in expanding this anymore, so let's plot this. Desmos. So we don't need this one anymore. So it's D2. So we'll call it just D because we don't have D here. F over. No, I don't want to do. F divided by. I guess I can't do F. F divided by. Okay, I probably can't edit here because like they have this stupid tool. I'll just open a new tab here to frickin' type it in, then copy paste it into Desmos. Otherwise, they're doing that weird stuff with the 1 over. So F over D2 F D times F times 1 minus df over d minus f. D times f over d minus f. Close, close, close. Okay. Add a slider for f. Okay. Why doesn't it like it? Y equals. Okay, yeah, y equals. This isn't the result I wanted. Well, actually, it is the result I wanted. So we can see that there's a bit of a divergence here. So first, if it's... Wait, what is f? It's actually getting small. What? What am I? F equals 1 is not what I want. F needs to be small. Yeah, okay, there we go. F is small, and then we're only looking at positive D. So as D gets bigger, then the size gets smaller. That's not right. I must have made a mistake. Right, so we're looking at this, right? We want to see how big this gap looks like to me as we get farther from the lens. And of course we should have like a flip also. I wonder if we're missing the flip. There's no flip. Oh, maybe the sign is wrong? No, I want distance to be this. 1 minus d1. 1 minus d1. d1 is this. Maybe it doesn't work when we're far. I don't know. Like if I flip this slider. Wait. Oh. Well. Okay, yeah, we are flipping. So, yeah. I think it's this slider is a little off. Also, yeah, so it does flip. Yeah, okay. I think this is right. Like, let's say f equals. Let's change the axis. 0 to 1. Okay. So we really care about the negative part. Actually, why is it so big? This doesn't seem right. Because when the distance is quite small, like when I should draw another drawing with my D's. D2. When D2 is small, then what happens? When D2 is small, D1 becomes... just plot it. Let's do a fixed f. I'm going to draw this. D2f df over d minus f. Do 0.1, just to make sure. 0.1 times D over freaking shitty shit, right? I guess, okay, whatever. We're gonna do this a fancy way. Okay, over D minus 0.1. Huh? That's I don't want this slider. Okay. Y equals. Okay, so we see this, which is that here, of course, we're getting some like infinite flips, but when D is so 0 is actually close. Oh, 0 is closer to the picture. No, this is right. 0 is closer to the picture, and when it's too no, what? I'm confused. So D1 is when it's close to 0. We're looking at the real life, right? D1 is close to 0, and then we expect like when D1 gets farther, and this is the non-flipped region. So when it's close to 0, the size should be. Can I undo that? Why is Y 0? This is the. Oh yeah, I guess it is 0. These approach 0. I think we should be getting a term that cancels that we're not getting to cancel. So this is correct. This approaches 0 at this rate, and then that's the D1. D1 and D2 at this they're just negative version of each other. Is that right? Yeah, I guess so. That's fine. And then we want H is D1 over D2. So this should converge to 1 if I just do this. Huh? Wait, what? At time 0, it converges to -1, which I guess is fine. Converges to -1. Is that right? And then it gets farther, and then it gets expanded. I think I want it to be +1, but that's not a big deal. That's just one sign change. So this is right, and then okay. And then this is 1. I want the size. So what's the size at 0 should converge to about 1 also, which is why I'm a little confused why it doesn't. So this D1 converges to 0. D1 converges. Size is H over distance. Distance converges to 1, and H converges to this. H over distance. H being D1 over D. What the heck? How did this happen? This is wrong. This is so wrong right here. This is not right. D1 over D2 is F over D2 minus F. This minus is critically important. I freaking dropped that minus. Okay, so we just dropped that minus in there. D2 minus F like this, and then put some parentheses, and this should do what we want. Oh yes, we're converging at 1. Okay, so here, F equals 0.01. Okay, that's fine. So now we can actually see that the size, can I actually undo that? Actually, the size is quite the same as just this thing, because we already have that 1 there. But it gets farther as we get farther. Now let's actually consider what's the size if we didn't have the lens in the first place at all. So h would just be constant, and we have the distance being not this thing, but just 1 plus d1. So it's just 1 over 1 plus d1. Okay, so it's 1 over 1 plus d1. Y equals. And it should be negative. So we can see that with the magnifying glass, it's actually like going in opposite directions, where this is right at the lens. And without the lens in place, it just gets smaller. It converges and gets smaller the further, smaller. Yet with the lens, it diverges, doing the exact opposite behavior of getting bigger. We can see that, again, if we look back at the picture. Look back at the camera. Right, so let's get a good angle. It's getting smaller. Smaller as it gets further. They're converging. Right, you can look, if I tried to measure these, like up here it's this wide. I mean, just, I guess if we just drew some vertical lines, right? Yeah, it's hard to draw some vertical lines. Okay, well anyways, you can tell they're getting narrower as it goes up. Now we put this here, and it gets, right, at the beginning part, actually the size stays about the same. It's unaffected, but it gets wider, extremely wider, farther back. Close up, right next to the lens, it's unchanged. Size is unchanged. But here, there's that massive divergence, massive wideness increase right there. Anyways, that was that. Kind of, I wanted to show a couple things and then do some math. This doesn't really answer the main questions of like, how do we make a lens in, how would we make a magnifying glass in a game? But it just kind of explains why it's difficult to do such a thing, and then why if you see a game that has some shitty magnifying glass, it will look really bad. I guess like if we wanted to do something like game development. Let me put this back on. Magnifying glass. Maybe build a caliper thing for future explanation. Oh, I have a caliper. That would be cool. Yeah, but like if you look at this one, this is like someone's demo of like,
if you're a
oh no. I need to figure out how to turn on ad block on this. But see, when you look at like his magnifying glass, it just looks like, it looks like shit. Look at this guy's shit. So it gets bigger when you get closer. That's so wrong. It's my last chance to go solar. No, I'm going to guzzle gas. I'm a gas guzzler. Vroom. But just look how wrong this looks. See, in his magnifying glass, when the glass gets closer, the object gets bigger. But it should be the exact opposite, where the farther you pull it, the bigger it gets until it flips. And of course, his will never flip. Anyways, this is part of the thing of, you can't even have there's no game that has a magnifying glass at all. Like in existence, I don't think anyone's ever made a real game that has one. It would be cool to make one. Maybe I will. I mean, I'm going to grab some calipers. Just 1 second. Got some garbage quality Chinese calipers right here. What about a game about measuring things with a caliper? Oh, that'd be cool. But I think it would just be really cool to make a game that's just like just grabbing a magnifying glass and investigating things. I just think that would be cool. All right, so let's go back here now that I got a caliper. Let me show you my caliper. Made in China quality. Battery doesn't even work. It's okay. We just need parallel lines. So we look here and we should actually be able to see the convergence quite easily, maybe. Of course, it doesn't converge all that much, but you can see these on screen, the calipers are parallel. And the lines there converge as they get farther. Now, I don't know if I can put the magnifying glass and a caliper thing all at once. It's going to be tricky. I don't have enough hands for this. I guess you can see it diverges, right? Anyways, that's that for that. I don't know. I just think it would be really cool to have a game that had any sort of. I know that there's ray tracing where you use ray tracing technology like RTX. What about the box, the caliper, then the glass? I'm not sure what you mean exactly. Like, what do you mean the glass? You mean the magnifying glass? Well, I mean, there's no point in putting the magnifying glass in the back, right? I mean, then you just see a magnifying glass, right? Right. You can see some calipers and you see a magnifying glass in the background and be like, okay, cool. But yeah, I mean, just being able to have something like this at all, in a game where you just even seeing it on the table, like something in the background. I mean, it backwards. Yeah, I guess you could have the caliper like that. That's a good idea. Yeah, I'm not going to mess with the calipers anymore. I don't have enough hands. Maybe next time. Yeah. But I think it would be a really fun game to just simply have a game. Well, of course you can do all this stuff with RTX on, with ray tracing and all that stuff. But it would be so cool to have a game where we just grabbed a magnifying glass and just looked at things. It would be the VR experience. It would be virtual. It would feel real. It would be real, just to play with a magnifying glass in VR and just watch things flip. It would be cool. Anyways, that's all I had for the stream. Unless you want to learn about telescopes. But I don't think telescopes are all that cool. Like a puzzle game thing. Yeah, I think it would be like maybe one of those like locked room puzzles or just some sort of, detective thing, but you got to use magnification. You got to use the power of like light. Why not an AR magnifying glass? You mean as merch? Would you want to buy an AR magnifying glass? I think, there's already the magnifying glass, the AM. There's always this one, this is the iconic one. So if you get if we just have like a cheap knockoff, you really can't make magnifying glasses a merch when this is the one that everyone knows. No. What do you mean, Gyro? What did you mean? Augmented reality. Augmented reality magnifying glass. That sounds hard. I think AR. I'm not really a fan of augmented reality. I just realized you didn't see any of that. I was showing this. Look at that. Look at that investigator right there. But yeah, I think it would be a fun fan game or something where you play as Amelia and you investigate things. That'd be cool. Anyways, yeah, I don't. I think AR is even. We already have VR being a little not ready for prime time. I think AR is even more towards that because, like, who even has augmented reality hardware? It's like we got the HoloLens, not related to HoloLive, the HoloLens, and only a few people have that. There's no real mainstream AR gear, so it's harder to make a game. Sounds fun. Yeah, I think it would be fun. I don't know. I would coming up with the actual puzzles is also going to be hard, but I guess just making the game that actually works and doesn't suck ass like this. Oh, did I even have this on this? Yeah, I did. I did have this on the screen when I showed this guy's trash video where the magnifying glass doesn't even work at all. Where if you phone thing can run AR, it's some limited capability. Yeah, that's true. Yeah, I guess it would be interesting to. You could have it on a phone. You could have something where it would be like your phone feels like a magnifying glass, where you where when you pull it, when you move your phone farther away, the stuff gets bigger. Now, I guess it would be cool, like to make your phone. Yeah, I mean, you already can do that, right? You can just use the camera app and zoom in, but it's true that. Right. It's, I guess, like in this guy's shitty Unity video, it's actually like just the same. Let me pull up this again. Right. So we have a phone and we put it in freaking zoom in mode, and like we can point our, which is like freaking zoom in, right? So the phone makes stuff big, right? But it doesn't look like a magnifying glass because the closer you get, the bigger it gets. Like it's not like a magnifying glass at all, is it? Focus on the phone. So, but it would be cool to make like a phone camera that acted like a magnifying glass, even though it wasn't. Let me zoom out this out a little. Actually, there we go. Right. So we see this phone. It like, you know, you do this and like it's actually just almost like, it doesn't feel like a magnifying glass at all, of course. Like pointing your phone at something and having everything look funnier. Well, I think certainly a funification beam would be cool, but of course, usually you do that with AR where you just slap anime girls all over everything. That's the true cutting edge of AR. Reality is augmented when you do that. But yeah, so you can kind of, you know, you can kind of use a phone as a magnifying glass, but not really. It would be cool if you could. I think it would be, well, you can use your phone to magnify things, but you can't use your phone as a magnifying glass because it doesn't do the thing. It doesn't do the thing where it gets big, you know? So I know you can, with your phone, you can do a rangefinder. Augmented reality, would it ever be possible to augment ourselves? Yeah, now that's a big question, right? Human, like, getting a third eye or something. Getting a third eye. 1 second. I'm not going to put this in OBS. Getting a third eye. I know what you mean. Augmenting ourselves. Just like this. Yeah, well, it's going to be a while, probably. Body mods already exist. Well, yes, but none that integrate with the body itself. You know, they have like putting a microchip inside you, but the microchip doesn't actually interact with you. It's just a microchip that happens to be inside you. I mean, you can put a microchip in a dead cat also, and it's a microchip in a dead cat. That's all it is, right? I don't think there's any meaningful body modifications that actually work. Maybe, I don't know. You can also say that you can get those artificial joints for people who have joint failure, things like that. Those are also kind of augmented bodies. Magnet and Pinky does. What is a magnet and a Pinky going to do, Gyro? I mean, it's just a magnet that's inside you. You'll never be able to pass through a metal detector again. Anyways, I think a magnifying glass app would be cool. Like it would just use your camera. What about a third hand so you could do the box caliper glass thing? Yeah, I could use a third hand. There's many times that I wished I had a third hand. I could really use one. Third eye, third hand, and I don't know what else the third I want. Third leg I think is not going to be too great. You know, they have the three-legged races. Three-legged race. The third leg I think is generally not particularly effective as far as I can tell. It lets you feel the magnetic field. Oh, I guess that's true. You can kind of feel which way is north. Oh, I can't watch these because the freaking ad block is not working. I'm not going to click these. But it generally seems like the people when they do the three-legged race, they do worse than a two-legged racer. So it seems like the third leg is not so effective. But I could use the third eye and the third hand. Those would be quite effective. I wouldn't mind having them. Yes, and then I guess feeling the magnetic field. So you can be like a bird and know which way is north without using your app. But can they carry more weight? Yeah, I don't really need more load bearing capacity. That's not my problem. Probably yeah. I'm assuming these three-legged racers, if they were loaded down with a big heavy load, the three-legged racers would probably win actually. Or is it the two minds that aren't effective? I don't know what you're talking about, Chiro. Clearly, we just see three legs. When you compare three legs to two legs, that the two legs is overperforming. Especially performance per leg, but even just raw performance. Anyways, I think that's all I had for today. I know we've been derailing a little bit. Yeah. This is some good ideas. Definitely got some good ideas. What about something like super soccer with three legs? Imagine the possibilities. Yeah, I guess so. Because right now when you run, you got two legs, and then you also have to like dribble the ball. I wish I could watch YouTube videos. You got to dribble the ball with those legs. You got to alternate between controlling the ball, and then running. But with super soccer, three legs, you could use one leg for the ball while the other two legs do the running. Well, anyways, I'm not a soccer player, so I won't be playing super soccer anytime soon. Well, so yeah, so today we learned a little bit about optics and about how things get big and small, and we drew this thing. We got this big tube, the tube, and it looks like math. I feel educated. I feel smart. Whenever I do something like this, I feel really smart. I hope you feel smart too from watching the stream, because even whether or not you understood it, you still watched the stream. So you can feel smart too. So we felt smart. I'll have some more streams. I'm probably going to do karaoke or something soon. We'll see. Keep an eye out for some more slots. And then there's also the finale, the actual final finale of StarCraft Brood War. I'm going to finally finish the Brood War. I thought I was going to last time, but I didn't. But anyways, that's all I had for today. Thanks for coming to the stream, and I will see you all later.